So that is the full constitutive model, full stress tensor for isotropic hardening. And unfortunately, that's probably the only one we can write down the solution in closed form to. That's not true. It's not the only one, but it's very difficult to be able to write down the solution in closed form, and that's why you see very seldom any closed form solutions to plasticity. They're almost always done in a computer. And to give you an example of one, and you'll see why, is that the case of viscoplasticity. Right, so in viscoplasticity now, the plastic part of the curve is a function of rate. So typically with increasing strain rate, plastic strain rate, that part of the curve increases, okay? Well, sort of the simplest model for this would be a yield function that looks like this. So now you have the quasi-static yield stress here. You have an additional parameter here, and you have an additional parameter here. And so these are fitting parameters that fit this sort of response curve that looks like this. Okay? Well, if we work through the same sort of details we did before, so now I'm going to differentiate this guy with respect to time. And then here I'm plugging in basically it's the same, my relationship for EP dot, but I take another derivative of it, another derivative with respect to time. So now I have a lambda double dot there. And so then I have S dot is equal to 2/3 n sigma y beta lambda double dot 1 plus beta square root 2/3 lambda dot n minus 1. And if I plug that into star, right, so send that to star, and what I get is an equation that looks like this. Okay, so earlier I could just explicitly solve for lambda dot and eliminate it, right? But now I have a differential equation in lambda. So in order to solve this, I have to solve this differential equation first for lambda, or lambda dot. So I have to actually solve this differential equation to get lambda, then I can plug it back in and eliminate it, right? And so that's why this is just sort of the next more complex case, and already we've approached something that, we have to go to a computer to solve. That's why you see very few solutions in plasticity. And I guess, so the next thing I'm going to cover, so everything up to now was this von Mises plasticity, J2 plasticity, motivated mostly by observations in metals. But of course we want to know about rocks in this class, and rocks are pressure dependent. We talked about that when we first introduced plasticity. So the next yield surfaces we're going to go to are pressure dependent yield surfaces. And we're just going to sort of, it'll be in a recorded video because I won't be here next week, but I'm just going to sort of outline them. We're not going to go into this much detail about how you actually return to the yield surface and all that. We'll take a look at that when we actually code these things up, okay? We'll just sort of conceptually look at what these yield surfaces look like, but they are not cylinders, right? They have a pressure dependence now. So the shape of the yield surface changes as you move up and down the hydrostat due to the pressure dependence. And these are what we use for geomaterials. So I guess just because of short time, I'll stop there.